Okay, we're one step, maybe two steps closer to where we need to be to solve the least squares solution for simultaneously estimating slope and intercept. So again, quadratic error function, sum of the squares of the vertical distances, simplified partial derivatives set equal to 0, and now we're going to solve these two linear simultaneous equations for m and b. Now, this one, the partial derivative with respect to b, we've already simplified in terms of b. So we know what to do now. We're going to take this, we're going to shove it into this equation. This will give us something in terms of m. Once we have m, we can then shove it back into here, and we get our b. Okay, well, let's just go ahead and do that. All right, so let's see here. I've got m times xi squared plus, what happened here? I see. Okay, there's the 1 over n times this whole term times that term right there, because I've substituted b for b, and then I should have a minus sum of xi, yi over here. All right, let's make sure we got all the terms right. So there's my b term right here. So this summation just carries over, m times the sum of xi squared. Good. We're going to take that, which is this whole thing right here, 1 over n times this expression, and multiply that by the sum of the xi right there, and then of course that just carries over right there. All right, let's do some simplifications here. I'm seeing some trouble with things here. I've got an m here and an m here, so it seems like the first thing I want to do is start pulling those together because I'm trying to solve for m here. So let me do a little bit of simplification here. So let's see what we're going to do. All right, there's that term. That's going to come straight down. Okay, now I've got a 1 over n times this whole expression here times that. But one of these things has an m in it, and I want that m. So I'm going to go ahead and multiply this out. So it's 1 over n times the sum of all the yi's times the sum of all the xi's. That's that term right there. And then I've got a minus m over n, that n came from right there, of course, times the sum of all the xi's times the sum of all the xi's. And then, of course, I still have that term drops down. So why did I do this again? Because I want that m. And I don't want it bundled up in this big gnarly mess here. I need to pull it out. And now I'm a little bit closer. I have 1m there, 1m there. That's m free. That's m free, so that's good. But I got to still do a little bit of work on those two terms right there. So let me go ahead and do that. So there's the m and the m that I now want to pull together. Okay, so what is this going to be? I have an m times the sum of all the xi squared terms here. Okay, so that's that right there. Minus, I have 1 over n times the sum of over all xi times the sum of all of xi. And notice the parentheses. So m multiplies that summation, and m multiplies 1 over n, and of course the number of points in our system, times that. Now, that's all the m's, and notice what I've done. I've got m times, well, this is a big, ugly looking mess, but what is it? It's just a number, just a scalar. Take all the xi's, you know what n is, take all the xi's, compute those summations, square them, sum them, but whatever you want, I don't care, and it's a number. And it's a number times m. That's great. Now, this is free of m, and that's free of m, so I'm going to push it over to the other side. So we get this negative sum becomes a positive sum, and that positive sum becomes a negative sum because we moved it over. And now we're basically home. I mean, it's a little messy, but we're home because we've got an m times a scalar value is equal to some other scalar value. Well, I can just bring that over to the other side now. So m is equal to what was on the right-hand side divided by what m was dividing. Done. I've got an m. Look, it's a little messy, I'll agree with that, but once I give you all the xi's and yi's, and you know how many data points there are, we can certainly evaluate this. Evaluate it, we get our m. Once we have our m, we back substitute it into here, and we get our b, and we have our least square solution. We went from quadratic error function to partial derivatives to solving two simultaneous equations in two unknowns. By the way, did anybody notice something funny here? I set off to solve an over-constrained system of linear equations. And to do that, I ended up solving a constrained system of linear equations in two unknowns, m and b. We just converted it into a constrained problem. That's it. Okay, good. Now, here we saw some intuition here that this looked like the offset between where the point was and where just the slope gets you. And so that was sort of a clean intuition. This one is less obvious there's an intuition, and it's not really that important, but I think it's good to have intuition for these things. So in the last segment in this lecture, I'm going to unpack this a little bit and see if we can get some intuition. Now, at this point, you must be thinking, this is a nightmare. I mean, doing least squares is a slog, and the chance of getting some of that algebra wrong has got to be extremely high, and the answer is it's absolutely true. Doing this strictly algebraically is a slog, and you shouldn't do it. You should do it linear algebraically, and that's what we're going to do in the last lecture, is to show that when we frame this in terms of matrix and vectors, the solution to this is much, much, much cleaner and much, much, much less error-prone, and generalizes to more and more unknowns. But you had to get through this just to see what the form is. All right, so one last segment on the intuition for what the least square slope looks like, and then we're going to see the nice, clean linear algebraic formulation. I'll see you in a few minutes.